All right, here we go. It says Leo is a 60% free throw shooter in a season. He shoots an average of 75 free throws. What's the probability that if he shoots 75 free throws, that he makes exactly 50? Okay, so this is a binomial distribution we saw yesterday. How would we calculate exactly 50? Using that's such high hopes for third period. They have been dashed yet again. If it's exact, if there's one outcome, then it's binomial PDF. Yes. And if it's more than one, more than 50, no more than 50, between 45 and 50, then we would do binomial CDF. Okay, so we're going to go through these quickly. Distributions binomial if it meets all four of the following characteristics. Remember, Ben. So it's binary. Each observation falls into one of just two categories, which for convenience we call success or failure. Independent, the N observations must be independent, meaning, what does it mean to be independent? Again, okay, one trial does not affect the other. All right, number, there is a fixed number of observations. That makes it binomial. If there is not a fixed number of observations, then it's a geometric distribution, which we will look at tomorrow. And in geometric distribution, you repeat the trial until you have success. However, in a binomial distribution, there must be a fixed number. And the probability of success, call it P, is the same for each observation. Okay, so if data meet the criteria for a binomial setting, then the random variable X that represents the number of successes, it's called a what? Anybody? Well, we statisticians are pretty creative. We call it binomial random variable. And the probability distribution of X is called a binomial distribution. All right, so kind of the shorthand notation for a binomial distribution is this. We've seen this notation before, right? With a normal distribution where we have the mean and standard deviation. Binomial distribution with N and P, where N is the number of observations and P is the probability of success on any one observation. And so in a binomial distribution, the values of X are the whole numbers from 0 to 9. So a binomial distribution always starts with 0, right? Because is it possible in a fixed number of trials to have no success? For example, if I am shooting 10 free throws, is it possible that I don't make any? Well, no, of course not. I'm going to make my free throws, right? But theoretically, like if Jack is shooting free throws, right? He might miss all 10, for example. Right? I mean, it's theoretically possible. Maybe not likely. However, so in a binomial distributions always start with 0 because in a fixed number of trials, it's possible not to have any success. However, that is defined. And then it goes up to the total number of observations, N. Okay, so which of the following are the examples of a binomial setting? Why or why not? Roll a fair die 10 times and let X equal the number of 6s. So this This is a binomial distribution. Okay, I'll tell you ahead of time. So let's go through and check. Success would be rolling a 6. Failure would be not rolling a 6. Are each of the rolls independent? Does this first roll affect the second roll? No. So independent? Yes. Fixed number of trials? Yes, and in this case equals 10. And then the probability of rolling a 6, if it's a fair 6-sided die, would be 1 out of 6, and that is the same for each roll. Therefore, this is a binomial distribution. Okay? Shoot a basketball 20 times from various distances on the court. Let y equal the number of shots made. Well, this one is not binomial. So which part does it fail? Okay, it is binary. Success would be we make the shot. Failure would be we miss it. Are the shots independent? We could probably argue that. Yes. However, what is not the case, since the shots are taken from different distances, the probability of success is not the same. Because a layup, for example, from right under the basket, there's a much higher probability of making that shot than a shot from half court, for example. So if the probability of success changes, then it cannot be binomial. So not the same probability of success. All right, and the last one here, observe the next 100 cars that go by and let C equal the color of the car. Okay, well, there's a fixed number of 100 cars, but this is not binomial either. Because it is not binary. Okay, if C is defined as the color of the car, there could be multiple colors of the car. So this is not binomial. All right, turn the page for me, please. Let's look at a couple of examples here. All right, in many games involving dice, rolling doubles is desirable. Rolling doubles means that the outcomes of the two dice are the same, such as 1 and 1 or 5 and 5. The probability of rolling doubles when rolling 2 dice is 6 out of 36 or 1/6. So if X equals the number of doubles in 4 rolls of 2 dice, then X is binomial with N equal to 4 and P equal to 1/6. So what is the probability that X is equal to 0? That is, what is the probability that all 4 rolls are not doubles? Okay, and so in this case, success would be defined as we roll doubles. Failure would be we do not roll doubles. And so what is the probability of not rolling doubles? Well, if the probability of rolling doubles is 1 out of 6, then the probability of not rolling doubles would be 1 minus 1 out of 6, which is 5 out of 6. And so here, the question asks, what is the probability that in 4 rolls, we get no doubles? So another way to write that would be the probability that we fail, we fail, we fail. I'm a loser, we fail. Okay, so how would I calculate this probability? Well, the rolls are independent, so we would do 5, 6 raised to the 4th power. So take your calculator and calculate that probability real quickly. And somebody help me out with that. Okay. So there's a little more than a 48% chance that we roll 4 times. We roll 2 fair dice 4 times and do not get doubles. And this says, what is the probability that X is equal to 1? So we need to, you don't have to do this every time. We're going to do this for the notes. But let's list the ways that we could roll 1 doubles in 4 times. Okay, so we want to find the probability that we have success, fail, 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 or the probability that we fail, success, fail, fail. How many of these are there? There's 4, right? Fail, fail, success, fail. And then the last one, probability of fail, 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 success. Okay, and in the formula that we looked at yesterday, that's where the combination comes from. How many different ways are there to have 1 success out of 4? In this case, there are 4 ways to roll 1 double and 4. Okay, so it would be 4, since there are 4 ways, times the probability of success, which is 1/6. And that 1/6 is raised to the 1st power because I had 1 success. And then the probability of failure, which would be 5/6. And the 5/6 is raised to the 3rd power because I have 3 failures. Okay, so calculate that for me. Put that into your calculator real quickly. And somebody help me out with that. It is that's what I got, 0.386. Okay. And so this is the formula for a binomial distribution, okay, where this part right here is defined as n factorial over k factorial times n minus k factorial, or this is the same thing. It's n choose k, where n is the total number and k is the number of successes. And so to be honest, you just need to be able to recognize that formula. It might pop up in a multiple choice or something like that. But for the most part, if we're doing a free response, use binomial PDF or binomial CDF. Okay, but let's look at an example here. It says when rolling 2 dice, the probability of rolling doubles is 1/6. Suppose that a game player rolls the dice 4 times, hoping to roll doubles. Find the probability that the player gets doubles twice and 4 attempts. Okay, so let me say this. On the FRQs, students lose points all the time because they don't write down stuff. Okay, so it would be very easy to just do binomial PDF. And I want to find that it's exactly 2 and write the answer, but you're not going to get full credit for that. Okay, because they care more about the process and how you get the answer than just the final number, if that makes sense. Okay, so like on the rubric, you've got to define certain things. And so what I'm saying, don't be lazy. Take the extra 2 minutes to write down the information. Okay, So I want to find the probability that X is equal to 2. What is X? X is going to be the number, okay, and success is defined as rolling double. So the number of doubles rolled and 4 attempts. All right. So n is equal to 4. Probability of success, P is 1 out of 6. This is a binomial distribution, right? All of this stuff down. Okay, and I'm gonna write this 2 ways for the notes, one with the formula and then one with binomial PDF. So we're gonna do 4 choose 2. Probability of success is 1/6. And 1/6 is raised to the, what power is it? How many successes am I trying to find? 2, so it's raised to the second power. And then times the probability of failure, which is 5/6. And then 5/6 is raised to the second power also, because out of 4, there would be 2 failures. Or we do binomial PDF. And then we've got 4, 1, 6, 2. And I would label these, okay? This is N, this is P. So take your calculator. And let's get these probabilities. You can do either one. Everybody remember where the binomial PDF is? We go to menu and then stats and then distribution and then binomial PDF. So somebody help me out with that. What's that number? 0.116. And then let's write a conclusion and context. Okay, just quickly. So there is about an 11.6% chance of rolling 2 doubles and 4 attempts. So part B says, should the player be surprised if he gets doubles more than twice in 4 attempts? Justify your answer. So here, I want the probability that X is greater than 2. And this is equal to the probability that X is equal to 3 plus the probability that X is equal to 4. There are 2 outcomes that are greater than 2. All right, so let me work this the long way, right? With the formula, it would be 4 choose 3 times 1/6 raised to the third power times 5/6 raised to the first power plus 4 choose 4 times 1/6 raised to the fourth power times 5/6 raised to the 0 power. Okay, just for the notes, we can do that. Or let's use our calculator. So we're going to do binomial. And this time, if there's more than 1 here, which there are, probability that it's 3 plus the probability of 4, we're going to do binomial CDF of 4, probability of success is 1/6. My lower bound, in this case, would be 3. And my upper bound would be 4. And then label these, okay, in the binomial CDF. Because sometimes they get picky about the notation. Okay, so N, P, lower bound, upper bound. So put that in your calculator. And what do I get?
0.16.
All right. So should I be surprised if that happens? Probably so, because this probability is very low. So let's answer the question that they asked. So let's say yes, because there is only about a 1.6% chance of rolling more than 2 doubles and 4. So we've got a single binomial random variable. We're going to use PDF. More than one binomial random variable, we use CDF. All right. So let's look at a couple of examples. A local fast food restaurant is running a draw a 3, get it free lunch promotion. After each customer orders, a touchscreen display shows the message, press here to win a free lunch. A computer program then simulates one card being drawn from a standard deck. If the chosen card is a 3, the customer's order is free. Otherwise, you got to pay up. So all 12 players on the school's basketball team place individual orders at the restaurant. What is the probability that exactly 2 of them win a free lunch? All right, so again, let's go through the process and write some things down. So I'm going to define X as the number of players that win a free lunch. Is there such a thing as a free lunch, though? I mean, we could talk about opportunity cost and all of that, but I'll leave that to the economics people, right? Let's just go with this example. Work with me here, okay? So N is equal to 12. Probability of success. How many 3s are there in a standard deck of cards? There's 4 out of 52. And since they are all placing individual orders, we can consider the orders independent of each other. So this is a binomial distribution. Write that down. And we want to find the probability that X equals 2. So binomial PDF. And we've got 12, 4 out of 52, and then 2. This is N and this is P. Label them, please. And put that into your little calculadora. And somebody got that? Okay. 0.175. And then write a summary statement. So there is about a 17.5% chance exactly 2 and 12 players win a free lunch. And so the next one says, if 250 customers place lunch orders on the first day of the promotion, what's the probability that fewer than 10 win a free lunch? So this is a separate problem, okay? So we're gonna define Y as number of customers that win a free lunch. And this time, N is 250. The probability of success is still the same. It's 4 out of 52. And we want to find the probability that Y is less than 10. Because it says fewer than 10. So just be careful here. This is binomial CDF. 250, 4 out of 52. And this is where you should be careful. What is my lower bound? 0. Right? Is it possible that nobody wins? Sure. And my upper bound is, careful, should be 9, right? Because it says fewer than 10. Probability that Y is less than 10. And label your CDF here. This is N, this is P, this is lower bound, this is upper bound. So take your calculator. Yes.
So wait, is this like different? Because I remember you were talking about how when you're finding the probability of like drawing an exact number, like the probability of like X being like greater than or equal to 10 is the same thing as X being greater than 10. Does that like not apply here? Because it's like it's like a fixed number of people. Like,
That's correct. This is a different type of distribution. Okay.
I got it.
All right. So, and the reason that the reason that it's different, okay, is binomial distributions are discrete, right? Whereas you were referring to a continuous random variable, and in a continuous random variable, it can take on any values in its domain. But here we are dealing with counts. Okay. All right, and what's this? This is 0.0061. Okay. So let's write a concluding statement. You can say there is a less than 1% chance of having fewer than 10 win a free lunch. Okay, and so that leads us to this common sense question. If a basketball player makes 75% of her free throws, the mean number made in 12 tries should be what? So what is 75% of 12? 9, right? Whew, good thing we have a calculator on the whole test, right? So, okay, we have formulas, and we got that by multiplying 0.75 times 12, right? So the mean of a binomial distribution is going to be n times p. And the standard deviation is going to be the square root of the mean times the probability of failure, where n is the number of tries and p is the probability. However, okay, so this is important. These only apply to binomial distributions. And these formulas are on your formula chart, as we saw yesterday, okay? But only binomial distributions. For the mean, we take n times p, standard deviation square root of that times the probability of failure. So this is find the mean and standard deviation for x equals the number of doubles in 4 attempts that follows the binomial distribution with n 4 and p equal to 1/6. So the mean would be 4, it's n times p, right? So 4 times 1/6. So that would give me 4/6 or 2/3. And then the standard deviation would be the square root of that. By that, I mean the mean times the probability of failure, which in this case would be 5/6. So 2/3 times 5/6, and then the square root. And that would give me 0.745. So 2 more examples here. Okay, in recent years, homeowners have become increasingly security conscious. So it is reported that almost 20% of Southern California homeowners questioned had installed a home security system. Suppose that exactly 20% of all such homeowners have a system. Consider a random sample of n is equal to 20. Then x, the number of homeowners in the sample who have a security system, has a binomial distribution with n 20 and p 20.2. Find the probability that 5 of those sampled have a system. Okay, so this is a binomial distribution. We've got n equal 20, p equal 0.2, and we are going to define x as number of homeowners with security system. And I want to find the probability that x is equal to 5. So this is one outcome. So it's binomial PDF. Label it. All right, we got n equal to 20, p equal to 0.2, and my x is 5. And so if you take that and put that into your calculator, you should get 0.175 again. So there is about a 17.5% chance, exactly 5, have a security system. And part B says find the probability that at least 40% of those in the sample have a system. So in this one, we still have n equals 20, p equals 0.2, and I want to find the probability that x is what? Okay, and how do we get 8? It's 40% of the total. 40% of 20 is 8. And it says at least 40%. So here it's going to be greater than or equal to 8. And so in this case, I'm going to use binomial CDF. And so we get 20.2 n and p. Lower bound is 8. Upper bound is 20. And if I put that in my calculator, you should get 0.032. So there is about a 3.2% chance at least 40% have a system. Okay, suppose that 30% of all individuals holding Visa cards issued by a certain bank pay in full each month. A random sample of 25 card holders is to be selected. The bank is interested in the number in the sample who pay in full each month. We can approximate the probability distribution using a binomial distribution. Find the probability that 8 card holders pay in full each month. Okay, so this is binomial. Binomial distribution. Okay, N is 25. Probability of success in this case is going to be 0.3. So I've got binomial distribution with 25, comma 0.3. You can also write it like this in the standard notation. And we want the probability that X equals 8. So I'm going to go to binomial PDF. Of 25, comma 0.3, comma 8. All right, and if you put that in your calculator, you should get like 0.165. So the probability is about 16.5% that exactly 8 pay in full each month. Find the probability that less than 2 pay in full each month. Okay, so here we want the probability that X is less than 2. And I didn't define X. X is probability, or excuse me, not the probability, it's the number of customers that pay in full. Okay, so here, this would be binomial CDF. With 25.3, this is N and P. What is my lower bound? Again, lower bound must be 0. And upper bound, if it's less than 2, the upper bound would be 1. So you put that into your calculator, and I got 0.002. Find the mean. It's N times P. So 25 times 0.3 will give you 7.5. And then find the standard deviation. That's going to be the square root of 7.5 times the probability of failure. And the probability of success was 0.3. So the probability of failure would be 0.7. And that would give you approximately 2.291.